Okay, sorry about that. Okay, words to know. Objective function. An objective function is a function to be maximized or minimized. A feasible region is a region in which all constraints are satisfied in a linear programming problem. And then linear programming is going to be a method of finding the minimum or maximum values of a linear function given a constraining system of linear inequalities. So basically what we're going to do today is we're going to look at different problems. And what these problems are going to have is they're going to have a variety of constraints, a variety of linear inequalities that we must satisfy. And when we go about graphing all these different constraints or linear inequalities, what we're going to find is a feasible region. This feasible region is going to help us to identify the minimum or the maximum value that we can use to satisfy all those different systems of linear inequalities, even if there's up to like 5. So that feasible region is going to satisfy all those different linear inequalities, thus making all those systems true, thus being the solution to our problem. And so we're going to go ahead and look at that today. So again, linear programming. Linear programming is a method of finding the maximum or minimum values of a linear function given a constraint system of linear inequalities. The function being maximized or minimized is called the objective function. And so basically, if we had a set of linear inequalities, now we're graphed, what we get is what we know as a feasible region. So in this instance, this green part would be considered our feasible region. It is considered a feasible region because it is feasible values that we can insert into our equation to make all those equations true. So feasible is just possibilities, possible regions that would make all of our constraints true. So let's look at applying constraints. So here's the first problem we're going to work through. This says a furniture manufacturer produces chairs and sofas. Each sofa requires 10 yards of fabric. Each sofa requires 20 yards of fabric. The manufacturer has 300 yards of fabric available to fulfill the orders. The numbers of sofas must be at least twice the number of chairs. So what you see here is that we have a variety of different constraints that we need to meet. We need to make sure that the number of sofas is twice as much the number of chairs. We need to ensure that we understand that the manufacturer only has 300 yards of fabric to work with. We must ensure that the chairs have 10 yards and that the sofas require 20 yards. So those are our different constraints we're going to meet. And so using these constraints, we have two variables. We're going to look for the number of chairs and the number of sofas that can be created, which will allow us to meet all these different constraints. So we want to identify what is the possible number of chairs and the possible number of sofas that we can create, but still satisfy all these different constraints that we have. Constraints being like limitations, things we have to meet in order to make this problem true. Okay, so here again is that problem, and here's me actually graphing that problem. Okay, according to the problem, what we get is a variety of different equations to work with. The main ones are going to be that the manufacturer has 300 yards of fabric. That being said, we know that it takes 10 yards of fabric for each chair, 20 yards of fabric for each sofa. And if the manufacturer only has 300, then we can use at least or at most 300 yards of fabric. Okay, so if he's making chairs and sofas, and we have a maximum value of 300 yards of fabric to work with, then we can use this equation to solve for how many X and how many Y's, how many sofas and how many chairs we can actually make out of all 300 yards of fabric. The next one we can identify, so the number of sofas must be at least twice the number of chairs. Well, that tells us the number of sofas, or Y, must be at least, so it can be greater than, but at least, at minimum, twice the number of chairs. Okay, so we have both of these different inequalities. And when we go ahead and graph these inequalities, what we get is this graph that you see right here. And we would just graph these on Desmos the way that we normally graph linear inequalities. And so given this information, what we're able to identify is a feasible region. Now, things to consider. In this circled area, we have a bunch of negative values, right? We have negative x's. And so this circle area actually tells us that we cannot use that region for a feasible area. Why is that? Because there cannot be a negative number of chairs, or there cannot be a negative number of chairs and sofas, right? We want to have at least one chair, at least one sofa. We want that to be greater than 1. And so because of this circled area, we wouldn't use that circled area because in the graph, the x and y values in the circled region do not make sense. There cannot be a negative number of chairs and sofas. That being said, that would leave us with this feasible region to work with right here. Okay, so now we've created a feasible region. And from that, I'm just going to go ahead and I'm going to map down each of our constraints. These are the equations that we just created. And we just identified, well, the number of sofas has to be greater than 0, and the number of chairs has to be greater than 0. Okay, so here are all of our different constraints. And then again, when you go ahead and when you put those on the graph, you'll get a feasible region. So as you can see here, we have like a polygon-like figure created. The polygon created by the constraints represent all the possible values that are going to satisfy the constraints in the problem in addition to the constraints we add. We call this the feasible region. So any values within the feasible region will satisfy the problem, what we're looking for. Okay. And so now we want to interpret, what is this feasible region telling us? Well, what this feasible region tells us is it tells us different things. Yes, everything in the feasible region will satisfy this problem. But whenever we have things mapped at the vertices, that will tell us our minimum or our maximum, or both, our minimum and maximum values. So the minimum amount of sofas and chairs we can create, and the maximum amount of values, the maximum amount of sofas and chairs we can create. And what are the vertices? So the vertices in any shape are going to be those on the outer region. So all these blue ones would represent our vertices. Okay. The other points would be those on the inside. So the vertices are going to be those on the outside, and then the other points are going to be those on the inside. And if I wanted to, I can plug it into my objective function. We'll look at how to create an objective function, but here we've just given it. So we're plugging it into our objective functions. The ones on the vertices are going to be at 0, 0, 0, 15, and 6 and 12. And so I'm just plugging that in to my original equation. So 50x plus 80y. And we want to see what that gives us. So let me go ahead and copy this down. Let's see.
I took a good look at it too. You don't look like you have to bump into a tablet.
Okay, so I'm going ahead and I'm just writing down that equation, and then I'm going to solve for it. And we're also going to test it on those other points. So basically, you're going to see what type of values does it give out.
I want to ask him for his Instagram.
Okay, so here we go. Here are our vertices. Now we're going to plug in our vertices values in. Remember that these are x's and these are y's. So x, y, x, y, x, y. Plug that into your calculator and you can solve. This one's going to be equal to 0. This one's going to be equal to 1200. This one's going to be equal to 1260. We can also test our other points Our other points here are going to be mapped at 0 and 5, 1 and 12, and 4 and 10. Again, these are going to be x, these are going to be our y's. And again, just plug that into your calculator and see what it gives you. And so what you'll notice is you do get different values, but whenever you look at your vertices are going to have the greatest possible value and the least possible value. So this would represent your minimum. So that would tell me that my minimum amount of sofas and chairs that I can create to satisfy all the constraints is for me to create 0 chairs and 0 sofas. That's a minimum, the very minimum. The maximum, however, the maximum amount of chairs and sofas I can create and still satisfy all my constraints are going to be 6 chairs and 12 sofas. And that would satisfy all the constraints that we had previously. Okay, so using this information, we will notice that the p-values at other points are greater than the maximum values or less than the minimum values. Okay, so the vertices are going to give you your maximum and your minimum. And then the other points, yes, they'll satisfy all those constraints, but they won't give you the minimum or the maximum value. Okay, and this is where we get to the vertex property of linear programming. It says if an objective function has a minimum or maximum value, it will occur at the vertex of the feasible region. So again, our feasible regions can be a lot of different shapes, but the vertices are going to be those that lie on the outside.
Yeah.
And so those points that lie on the outsides are going to be your minimum and your maximum values. They're going to represent the minimum and the maximum values. Okay. And so we're going to look at some more examples. So again, here's another problem. And from this problem, And so from this problem, what we're going to be able to do is, first thing we want to do, we get our problem, we want to identify our constraints. We want to put our constraints, all of our different constraints, into a graph. So graph all those linear inequalities. And based on that, we're going to get a feasible region. That feasible region is going to tell us all the possible values that would satisfy our objective function, what we're looking for, basically. And then the ones at the vertices are going to help us identify the minimum values that would satisfy those constraints and the maximum values that would satisfy those constraints. So basically that is what linear programming is, but we'll look at another example. So here we have a wide variety of information. It says a manufacturer has 2 machines X and Y that produces 2 projects, A and B. Machine X produces 4 units of product A and 5 units of product B per hour. Machine Y produces 3 units of product A and 10 units of product B per hour. The cost to run machine X is $22 per hour, and the cost of running machine Y is $25 per hour. Given this information, we want to identify how long should each machine run to minimize the cost of filling an order at least 90 units of product A and at least 150 units of product B. So there we have another constraint. But what we're going to look for is the value that would minimize the cost. So we're looking for that minimum value. Well, because we're looking for a minimum or maximum value, we know that whenever we graph our functions, what we're going to look for is the vertices. We're going to look for the vertex that represents the minimum. But the first thing we need to do is we need to create those equations and, the minimum. First thing we want to do, create those constraints, graph those constraints, look at the feasible region, and then from there we'll be able to identify our maximum or our minimum value. So here's just a condensed version of everything we looked at. Machine X, what it creates, machine Y, what it creates, the cost of machine X and the cost of machine Y. right? So that's everything just kind of condensed for us to see it. And what question are we looking for? We're looking for how long should each machine run to minimize the cost of filing an order, at least 90 units to produce A, and at least 150 units of product B. Okay. And so here's the equations that we would create that demonstrate those constraints. Okay. So I'm trying to see if we can product A. Okay. So product A, I'm trying to identify what my machine will create. It says I want 90 units of product A, so at least 90 units. And it tells me that machine X produces 4 units of product A, and machine Y produces 3 units of product A. So that's how I get that constraint. Now I'm going to look at product B. So product B, I know I want at least 150 units of product B. That's where I get that. And I know that machine X creates 5 units of product B, and machine Y creates 10 units of product B. Okay, so that's how I get this constraints. I also know that I can't have negative hours because I do have to run that machine a couple of hours. So I cannot have negative hours. I have to have something greater than 0. Okay, and once I go ahead and map those constraints, I get this graph on the side. So I've mapped all those different constraints that I've identified. And what I notice is I have a variety of intersection points, okay? And so my feasible region is going to be this region over here, this green region. And so now I want to identify the vertices of that region. Here are my vertices. Here's 1, here's 2, and here's 3. Those are my vertices. If you think about it, say that I have, let's see. Here, I can go ahead and show you better why those would be the vertices. Sorry, hold on. I'm trying to get it. I keep messing that up. Okay, say I took out that shape, and I can go ahead and just draw the entire shape. It's not going to be perfect, but there's the shape. And so all my vertices of that shape would be these. All those edge parts of that shape would be the vertices. And so because of that, the vertices that I see on this graph are going to be these 3 right here. Okay, so now I have my vertices. Remember that I'm trying to find the minimum. How long should each machine run to minimize the cost of filling an order of at least 90 units of product A and at least 150 units of product B? So I'm trying to identify what that minimum value is. But what I know is I can find my minimum and my maximum value by looking at the vertices. So here I have my vertices listed out. And now I can plug this into my objective function. My objective function is going to be cost. I'm trying to minimize the cost. And if I'm trying to minimize the cost, I know that the cost to run X is $22 per hour and the cost to run Y is $25 per hour. So $22 for X and $25 for Y. That is my objective function. So now I can plug my intersection points into that objective function. Again, because I'm trying to find the minimum cost, or how long should I run these per hour to minimize the cost. Okay, and I'm going to get that from my vertices. So 0, 30, 18, 6, 30, 0. Plug that into my calculator. And I get 750, 546, and 660. Which one is the minimum cost, which is the least amount? This cost right here. And so that would represent my minimum. Again, I'm trying to find what is my minimum cost. How long should each machine run to minimize the cost of filling an order of at least 90 units of product A, and then it leaves 150 units of product B. So this is my minimum. And so that tells me that the minimum cost is $546 and occurs at 18 and 6. And what this is telling me, 18 hours at machine X, because that's my X function, and 6 hours at machine Y. That would satisfy all these different constraints, but also represent the minimum cost. Okay, any questions?
No, ma'am.
Okay, so I'm just going to go ahead and list what our steps are. So the first thing, we want to read the problem, right? We want to identify the constraints. And write them as linear inequalities. Then you want to graph those inequalities to find the feasible region. Graph inequalities to identify feasible region. You want to write the objective function, or sometimes it's given to you. And then evaluate the vertices. So basically plug the vertices into the objective function and see which one would represent your maximum and which one would represent your minimum. And depending on what the question is asking, for example, this question is asking us to find the minimum, then that will help you solve your problem. So evaluate the vertices. So those are the steps to solving a linear programming equation. Okay. So now we're just going to look at one more very quickly. This says, suppose you have $16,000 to invest in 3 stocks, A, B, and C. Stock A is the lowest risk stock that has expected returns of 4%. Stock B is a medium risk stock that has an expected return of 5%. Stock C is a high risk stock that has an expected return of 6%. You want to then, or you want to invest at least $1,000 to each stock. You want to balance the risk, you decide to invest no more than $7,000 in stock C, and to limit the amount invested in stock C to less than 4 times the amount invested in stock A. You also decide to invest less than twice as much in stock B as in stock A. How much should you invest in each stock to maximize your expected profit? So what you notice here is we have a wide variety of constraints. But for each of these individual constraints, we can go ahead and we can create a linear inequality to represent them. Okay? So let's start at the very beginning. We know that we want to invest at least $1,000 in each stock. That means that I want to invest at least $1,000 in stock A, at least $1,000 in stock B, and whatever you invest in stock C is going to be the total amount you have to invest. You have $16,000 to invest, minus how much you invested in stock X and how much you invested in stock B. But it will also be, of course, greater than 1,000 because you want to invest at least 1,000, at minimum 1,000 in each stock. Okay? X again represents that of stock A. So how much I've invested in stock A. Y represents stock B, how much I've invested in stock B. And 16 minus X minus Y would represent the amount in stock C. And the reason I'm writing this as 1 and 16 just to simplify it, but it is in fact in thousands. Meaning that if I really wanted to represent it, I would put, he wants to invest at least 1,000 in each stock. At least 16,000 he has total, and 1,000 in this stock. But I just minimized it, simplified it so that it's easier to work with. I could represent it like that, but I can just keep in mind that it is in fact in thousands. So that's what I chose to do. Okay, so now I labeled those first constraints. Now I want to go ahead and identify what we're trying to do. We're trying to determine how much should you invest in each stock to minimize your expected profit. Well, we're trying to maximize profit, right? We're trying to maximize my expected profit. So write a profit function P that will identify how much profit we are going to be able to make in these investments. Well, we do have an expected returns percentage for each stock. So basically that's the amount of expected profit we're going to make for each stock. So we're trying to make an objective function that represents the profits. What we're going to go ahead and do is we know stock A, you're going to get 4% returns. So 0.04, I'm putting that in decimal, would represent the amount of returns that I get in stock X or A. 0.05 would represent the amount of returns that I'm going to get in stock B, or I've chose to represent it as stock Y. And then in stock C, I'm going to get 6%. So that's going to be 0.06 expected return. And remember that I represented stock C as being equal to 16x minus Y. Okay, so there I've created my objective function. Basically, I'm taking this information that I have here. A is represented by the value X, B is represented by the value Y, and 16 minus X minus Y represents the stock C. So that's what I'm just transferring over here to create an equation that is graphable. Okay, and because I'm looking for profit, I'm going to use the information about my expected returns. So that's my expected profit for each of those different investments. So now I have my objective function. And I have a little bit more constraints to deal with. So I've basically dealt with most of these constraints, but I haven't dealt with this set of constraints. And so I want to go ahead and deal with those. So I've created most of my constraints, but I still have more to do before I go ahead and graph this. The first one says, you decide to invest no more than 7,000 in stock C. So stock C, we know is represented by 16 minus X minus Y. We want no more than 7%. So it can be greater than or equal to 7. And to limit the amount invested in stock C to less than 4 times the amount invested in stock A. So that tells me it's going to be limited to 4. And then I want it to be less than twice as much in stock B. So Y obviously has to be greater than 2. Okay. And again, I know that in stock A, I need to invest at least 1,000. In stock Y, I need to invest at least 1,000. Okay. And so now I have all my different constraints created, and this is what I can go ahead and graph. When I graph it, when you graph it, you'll get a shaded area. I just didn't copy it here, but your shaded area will look like right here. Okay. So that is your feasible region. That will make all these different constraints true. And so based on this, I want to identify how much should you invest to maximize your expected profit. Remember that the maximum and the minimum value are going to be on your vertices. 3 and 6, 5 and 10, 8 and 1. This is 14. Okay, and so basically what you want to do to find your maximum value is you want to plug these values into your objective function, which is this function we created, and see which one will give you the maximum profit. And that would be your answer. Okay, so you're basically doing the same steps, but in this instance, you are going to go ahead and identify those constraints, and in this instance, you're finding the maximum value, where in the other one, we're looking for the minimum value. Okay? But we'll go over some more examples tomorrow. But this is basically what we reviewed. We learned that linear program problems consist of maximizing or minimizing a function within given constraints. Graphing the constants form a polygon called the feasible region. An objective function is written to represent cost, profit, etc. So what are we looking for at the end? What is the problem we're trying to solve? The maximum and minimum values of the objective function always occur at the vertices of the polygon containing the feasible region. And here are the steps to solve that linear programming equation, which we just went over. Read the problem carefully, write a system of linear inequalities, graph the systems of inequalities to obtain the feasible region, write an objective function, and then evaluate the objective function at each vertex to solve the problem. Okay. But like always, we'll go over some more example problems tomorrow. If there's no other questions, you guys may log off, and I will see you guys tomorrow. Bye, guys.
Bye, Miss.